Hi folks, so for Lab 8 I'm actually recording this video outside. I'm sitting outside because I'm actually sitting on the periphery of the patio of a particular restaurant. And I'm doing that because I actually feel that some of you will probably find yourself in a similar position as me as you're taking data for your final project. The idea is you might be sitting here, you might be watching customers as they come into the restaurant, maybe watching what they do when they're inside the restaurant, and then as they move out of that restaurant, or maybe it's an airport, or maybe it's a bank. But what this lab is going to do is hopefully provide you some insights into how you design your data collecting experience, which data to collect, how to collect that data, and then what to do with that data once you have it quantified, say in a spreadsheet, and then how you can use tools from Arena to simplify the process in turning it into an input model that you can then implement in a simulation. And of course, once it's in the simulation, you can try different what-if scenarios to try to come up with maybe a better operations plan for the system that you started at, a restaurant like this one. So let me get out of the way for the rest of this. I'm actually going to split this video up into 3 parts. So you can watch these parts however you'd like. You can skip ahead if you'd like. The first part is going to be a little more abstract, and we're just generally going to talk about what you should do when you're taking your data, like you might do, say, next week for your final project. Which data to collect, which data should you be careful not to collect or not to group together, and in general, how are you going to then take that data and then come up with a good abstract probabilistic model that best represents that data. So that will sort of start in here in video 1, and then in video 2 it's going to be a tutorial of the input analyzer, a tool that comes with Arena that helps you take data like the data you'll collect for your final project and then turn them into these probabilistic input models you'll use in your stochastic simulation. And then in the final video, we'll actually talk about what's required of you for this lab, so that lab experience. And there is a spreadsheet that comes with this presentation that you should be able to find on Canvas that will accompany that as well. All right, so let's move forward to this first portion. So we're focusing here on the general practice of gathering data and building at least conceptual or abstract input models, and then we'll make it more quantitative in the second video. So imagine, for example, you start at a fast food drive-through with 2 stations for ordering. So in that you have customers, those are probably your entities. You've got resources, let's say those are the 2 ordering stations during the drive-through. The customers have an arrival rate, and then there's a service rate. How long does it take for them to provide their orders, for their orders to be taken, and then for their food to actually be prepared. So we can kind of view this diagrammatically as customers arrive. They find themselves in a queue waiting for service, waiting behind other customers who arrived earlier. And then finally, those customers at the head of that queue get access to resources. And so let's say here there's only 2 resources that are available, but maybe 3 additional ones that potentially could be available. So that's kind of what we're kind of depicting here. Once those customers have given their orders and their food has been finished, then they can finally depart. So this is the basic structure of many systems, not just a fast food system, but like I said, banks, even maybe airports, etc. So the question is, how do we collect data for this model? What's the right data to collect, and what are the pitfalls we might get into? So one of the problems that a lot of people have is they treat these systems as black boxes. They sit, like I am, outside the system, and they just watch customers as they go in, and then they watch customers as they come out. So there's an arrival rate, and there is a single service rate, which represents the entire time that a customer spends inside the service. Now, that's bad because the internal details matter. So if we think about it, when a customer arrives and they go in, there's that queue that they have to deal with. They might have to wait behind lots of other customers. And if we're just sitting outside the system, we don't see all those other customers inside. So we think we're measuring activities, but in reality, we're measuring delays. So the inside details of exactly where are the activities and where are the delays matter. We really need to see where the customers interface directly with the resources. So the resources are like the people taking the customer's orders. The resources are the people making the customer's food. If there's a significant amount of time where customers are just waiting behind other customers, we might need, be interested in that to validate our model later to see if our model is generating the right delays. But we really can't measure the time that a customer is waiting behind other customers as if that's part of the time it takes for a customer to make their order. So remember the difference between a delay, a conditional wait, and an activity, an unconditional wait. So the better approach is to actually go into the restaurant, to go into the system and see the steps that a customer has to go through. So collect data on individual service times and how servers depend upon each other. So a customer might go in, they might wait in a long line. Eventually they get to go and maybe they provide their order to one cashier or another. They might pay for that order. It takes a certain amount of time for all of that. And then they watch their order getting made. And their order might go through multiple steps, and those steps might depend upon each other. But their order isn't actually completed until it goes through all of those steps. So each one of these little arcs represents a service time. And that service time is something that you'd want to collect data on. So how long does it take for them to make the order? How long does it take for the order to get started and go through step 1, and go through step 2, and go through step 3? And then each one of those steps gets modeled as a different probabilistic distribution. So we need to refine our data collecting. That is the better approach. The even better approach is to additionally measure the customer's total time in the system. So if you were just measuring their total time in the system, that would be a really bad approach. It would be almost useless. But if you record all of those individual service times, those will go into your simulation model, and you'll then be able to simulate a model of the real restaurant. And that model of the real restaurant is going to generate distributions of total times in the system. And that you'll want to compare to the real total times that people spend in the system. If those two things are very different, then that means that your model of the system is probably missing something important. It might be missing a service time. It might be missing some part of the process that contributes to the total time in system that you're not seeing there. So that's kind of all of the things you want to take. You want to take these inputs as well as these outputs. So other things that you might want to observe while you're inside this system are resources cross-trained, for example. If you remember in the Lab 7 call center example, there were a number of resources that took calls, but some of them were only trained on certain products and not others. And so that cross-training was modeled. If you go into a coffee shop, you might notice that the person taking the orders sometimes has the ability to actually make the coffee too. But sometimes if you go into, let's say, a particular fast food restaurant, there might be a cashier who knows how to make certain things, let's say the salads, but they don't know how to make some of the more advanced options. And so you might want to group your orders into different types, and then those different types might have different resources available based on the number of idle resources that are cross-trained on those particular types. Other things that are really important that we'll talk about a little bit more here is do the arrivals change throughout the day? Right now, I see that hardly anyone is arriving at this particular location. The arrival rate for this hour of the day is relatively small. But at this particular location, if I came back at lunch, it would be very busy. So it would be wrong for me to group all of those arrivals together and pool them together. I would end up making the lunchtime hour seem like it had less arrivals per unit time, and I would end up making this hour of the day make it look like they have much more arrivals. What I really need is to model those times separately so that I have a high arrival rate at the lunchtime and a very low arrival rate now. Do resources change in quantities? Right now, I can guarantee that if I look inside this restaurant, that hardly anyone would be working. But if I come back at lunch, I'll see that a lot of people will be working. So I might have multiple cashiers at some times a day and almost no cashiers. In fact, it might be the person making the food is splitting their time between being a cashier and making the food at other times of the day. So make sure you take those into account so you can adjust your resources appropriately. Then, again, going back to validation, do take data on how many customers are waiting in line at any particular time. How often are the resources busy? How much time do the customers spend in the system or spend in certain parts of the system? Although you may not use those to build input models that you'll directly build inside the simulation, once the simulation is done, you'll be able to ask the simulation how many customers were waiting inside the simulated model, and does that match what we saw in the real model? And that helps validate our model. Now, I mentioned just a second ago about these arrival rates, and sometimes you can group these arrival rates together, and other times you really need to leave them separately. It would be a bad thing for me to group the arrival information from this time of day with a lunch period. But when can I group things together? So that's the question of pooling. When can I take a small set of data and group it into other small sets of data to increase the amount of data I have, which will end up making for a better fitting model? But I don't want to pool too many things together because I end up, even though I might get more precision in my estimates, the accuracy will decrease. So how do I maintain a high level of accuracy while also increasing precision? And that's the real question here. So now I'm going to shift away from a restaurant example and imagine, say, an airport example. So I have counts of arrivals that come into an airport. Now, it might not be feasible for you to record the exact time someone arrives to an airport, but I might be able to count how many arrivals I get in any 10-minute period. So that's what I've shown up in this spreadsheet here. Let's say on a Monday from 9 a.m. to 10 a.m., I group those into 10-minute intervals. And so I have 10-minute intervals. And so this 10-minute interval, I only got 1 arrival. This one, I got 5. The next 10 minutes going into the half hour, I got 6, and so on. So I have all these 6 counts spanning over the 60 minutes from 9 a.m. to 10 a.m. on a Monday. And I could do that on a Tuesday, a Wednesday, and so on. I could do that for the 10 a.m. hour as well, the 11 a.m. hour, etc. So these are counts in groups of these 10-minute intervals. So I'm going to assume, based on my prior experience, that the arrival rate to the airport doesn't change much within this 60-minute window. So already ahead of time, I'm assuming that all 6 of these I can pool into one estimate of an encounter rate. Let's say an exponentially distributed inter-arrival times with a constant arrival rate, where that arrival rate is fixed for just this 10-minute interval. So I could fit a Poisson distribution to these counts. Now remember, there is a relationship between a Poisson distribution and an exponential. And that relationship is that the parameter I fit to the Poisson distribution is equal to the exponential arrival rate times the interval length. So I might find that there's, say, an average of, well, let's see, I could do this number here, 1 plus 5 plus 6 plus 9 plus 6 plus 4 divided by 6. So this has an average number of arrivals of 5.17 arrivals per every 10 minutes. So if I were to fit the best fitting or maximum likelihood Poisson to this, it would have an alpha parameter. The parameter of the Poisson would be around 5.17. So that would mean this Poisson is going to generate random numbers that are around 5.17, representing the rough number of arrivals that I get in every 10-minute interval. If I were to divide that 5.17 by 10 minutes, so 5.17 divided by 10, I get 0.517, which is my encounters per minute. And that number of encounters per minute I could use to build an exponential that generates actual inter-arrival times, the actual time durations between arrivals. So I've shown here that I can go to the airport and I can count the number of arrivals in a 10-minute interval. And then in my simulation, I can actually generate arrival times instead of arrival counts by this simple conversion where I divide by the length of the arrival time. All right, but I wanted to get back to pooling. Using these 6 data points for this one little interval from 9 a.m. to 10 a.m. in this Monday region here does not provide me a lot of confidence in my Poisson parameter estimate because it's only 6 data points. So there's going to be the confidence interval on this alpha parameter, on this 5.17 is going to be very large. However, I might notice that every weekday, Monday through Friday, from 9 a.m. to 10 a.m., I get roughly the same sorts of numbers. In other words, if I were to fit a Poisson to Monday's 9 a.m. interval or Tuesday's 9 a.m. interval, I would get roughly the same average number of encounters per 10 minutes. So the idea is maybe I can pool all of the 9 a.m. hours together. And maybe I can pool all of the 10 a.m. together. In other words, maybe I can pool across days. So if I've got a data set here, Monday through Friday, and I've got 6 counts every hour, so 1 per every 10 minutes, then maybe I can come up with an encounter rate lambda 9 for the 9 a.m. hour. Maybe I can come up with an encounter rate lambda 10 for the 10 a.m. hour, and so on. And these encounter rates that I get for all of these different hours are just going to use, instead of 6 data points, they're going to use the 30 data points that come from me collecting across all 5 days, 5 times 6. Now I do not want to pool across hours. I don't want a Monday encounter rate and a Tuesday encounter rate and a Wednesday encounter rate and so on, because it is unlikely that the encounter rates are going to be relatively constant across all hours of Monday. And it also seems strange that I would need a different encounter rate for Tuesday than Monday because they're both weekdays. So those are examples of how I might want to pool across days within an hour, but not across hours within a day. And by doing that, I get more data to make my fit better, and I actually get a simpler model because I may not have to actually simulate every hour of every day. I can actually now just generally have a weekday model where I have to simulate every hour, but I actually don't care whether it's a Monday, a Tuesday, a Wednesday, and so on. Every weekday has got the same distribution across the hours. All right, now that we've covered data collection, let's imagine that you've done a lot of data collection and you come back and you have a spreadsheet full of data and you're not quite sure what to do with it. How do you create good input models? Now, in the last particular case, the data we collected were on arrivals. We assumed that occurred independently of other arrivals. And so we already kind of knew ahead of time we were going to borrow from the Poisson process. And so we were going to take these counts of arrivals, model them as a Poisson random variable, and turn that into an exponential random variable that on our simulation model could actually generate individual arrivals, so by generating those inter-arrival times. Now, we might have data that we just simply do not have that intuition about. So how do we create those input models? Well, the first thing we do is we look at the data and we say, are they discrete or are they continuous? If they're counts of arrivals, they're discrete. But I can tell you not all discrete data will end up looking like counts. In other words, discrete data don't need to be integers. I can roll a 6-sided die and it can come up with words, or it can come up with irrational numbers. And so it's not just the outcomes themselves, but it's the frequency of those outcomes. And so if I were to take a histogram of the outcomes of my data, then I might see something that looks like what's on the left or what's on the right. Now on the left, notice that I basically get only 4 outcomes, and there's huge gaps in between those outcomes. So it looks like I get, 2, maybe 3.14, 5.5, and 6.75. Compare this to on the right, where if I were to look at my data, I effectively get every outcome from a continuum from 0 to infinity. And really, any separation here is just kind of artificially generated by the histogram. Here, these are real separations in the data. I never get outcomes in between these two. But over here, I can get every outcome from 0 through infinity. And so that's kind of the key characteristics you want to look for when you're trying to tell the difference between discrete data and these continuous data. So look for how many peaks occur. Is there sort of a countable number of peaks, and are there large gaps in between them? And if there are, you can then estimate the probability mass for each outcome just by proportion data. So like in this case here, for this outcome that just happens to be pi, I took 10,000 samples and about half of them, 5,045, came out to this outcome. So I'm going to estimate the probability of that outcome to be 0.5045. Now ideally, if I look at this distribution, I'll recognize it. And I will say, you know what, this might look like a Poisson distribution or a negative binomial or a geometric, in which case I don't have to actually estimate these proportions directly. I can estimate the 1 or 2 or maybe 3 parameters that come into that distribution. And that's actually a good thing to do if you can, because especially in the case of rare events, you might not witness all of the outcomes, but if you were to watch long enough, then you would have eventually seen some outcomes that didn't occur in the very frequent outcomes that you did see. And if you were to fit, say, a Poisson or a geometric or whatever, then you might fit them from those frequent outcomes, but then that distribution will end up generating rare events that you didn't see in your real data, but are maybe better representatives of your real system. And so it's always better to find the general, more abstract model that you can fit with 1 or 2 parameters than it is to fit proportions and then only show the outcomes that you did see in your real data. Now this makes it hard because if you look back at these shapes, you might not recognize these shapes, and you might not also recognize the spacing between these shapes. It might be that the model that you're familiar with actually labeled these outcomes as, say, 0, 1, 2, and 3. But just because of the real world system, those outcomes end up coming out as actually things like 2, pi, 5.5, and 6.75. So the labels of the outcomes might be different than the labels that you're accustomed to, but so you sort of have to start seeing the shape. It might also be that the organization of these things, like it might be that this outcome, there's really no reason for it to be in between these two outcomes, that maybe if you relabeled it, it would have showed up on another side, and then it might have made more sense as a Poisson or a geometric or some other discrete random variable. So it's tricky to be able to come up with these general models, but hopefully over time, as you become more familiar with these discrete random variables, then you'll be able to spot them as you start looking at these histograms. So homework G3 is an example of where we've told you that Poisson is the right family, but what we're trying to build is your intuition to the point where you can come up with those families on your own. All right, so if you don't recognize the family, you look at the histogram, you can estimate these proportions, and then you come up with these probability masses. And I'll show you then how to implement those in ARENA without an a priori model like knowing it's Poisson ahead of time. Now, another way you can get these proportions is by looking at an empirical cumulative distribution instead of the histogram. So these are the things where you take your data, you sort your data, and you plot the sorted values on the x-axis against their rank, their normalized rank on the y-axis. So here only 4 outcomes occurred: 2, pi, 5.5, and 6.75. And we got a bunch of 2s, and so they all kind of so they were all grouped together in the ranking. So rank 1 all the way up through roughly a quarter of the way, or I guess a fifth of the way up here, and then after that it was pi, for about half the outcomes, and then 5.5 for another fifth of the outcomes, and the rest of them were 6.75. So this is our empirical cumulative distribution function. Now, the step locations represent the outcomes, and the heights of these represent the proportions. Now then, you might say this is a weird way to look at it, and you might prefer the histogram, but the nice thing about the cumulative CDF is you don't accidentally bin outcomes together like you would in the histogram. So in the histogram, if you just happen to choose bins that were at very large widths, you might accidentally bin, say, 5.5 and 6.75 together into one big outcome that you might call 6. Now, if you just plot the empirical CDF, I didn't do any binning to get that CDF. I just plotted the raw data, and they just naturally aggregated together because I sorted them. So the empirical CDF has this advantage where you don't have to worry about binning. The only downside is that it can be kind of difficult to see maybe where these step heights are. So just things to consider. Now, either way, with either one of those, you end up getting proportions. And so here are my outcomes: 2, 3.14, 5.5, and 6.75. Inside Arena, if I don't have any formula like a Poisson that I can just simply implement inside Arena with a single parameter, and I have to use the probability masses, the raw probability masses directly, I can use the disk function inside Arena. But I have to use that cumulative distribution inside here. So I notice the range here. These are my 4 outputs, and they show up here. And the cumulative probabilities show up here. So notice this is like in my empirical cumulative distribution function, the level of each step corresponds to the the odd arguments here. So 0.1939, that's right here. 0.6984, that's here. 0.8983 is here, and then 1.0 is up here. So there, I've got 4 outcomes, 4 cumulative probabilities. I can enter that directly into Arena, and Arena will then be able to draw random outcomes that have the same frequency distribution as my real data. Now, what if the data come out looking continuous, like this histogram right here? So we recognize continuous data because basically most bins are adjacent to all the other bins, and there's typically very few gaps. So one thing I want to do to sort of put me in the right ballpark of picking a good continuous distribution family is to ask things about the data. Are the data infinite? Do they go in both directions? Am I just as likely to see negative 5,000 as I am to see positive 5,000? Are they semi-infinite? So in other words, like in this data set, it looks like I never get negative values, but I can get any positive value, although these positive values are very rare. Are they bounded? Imagine if I had a histogram where it only went from 0 to 0.6 and I didn't see any values greater than 0.6. All of these things help me figure out what type of random variable I might want to use to do my fitting. Now, with that intuition you get from coming up with a likely family, you can then combine that with a tool like the input analyzer that we'll learn about in part 2, and it will then be able to provide you the best fitting member of that family of distributions for the data set you have here. Now, if you can't find any good family, you, like the case for the discrete distributions, can then generate an empirical distribution that Arena can sample from. So, if I have my empirical CDF here, for example, of my data set, we learned that for a discrete random variable, I can use disk. Well, I can take that same one and use cont with the exact same arguments here, and what it'll do is it will take that cumulative distribution, and instead of having these flat stair steps, it'll link them with these lines here. It just linearly interpolates between all the corners of the empirical cumulative distribution function. And that then allows Arena to sample from the entire distribution from 2 to 6.75. And just in general, as we'll see in, I think, part 2 of the video, if I have any kind of discrete-like description or representation of my data, I can turn them in to a disk or a cont. So let's say I've got 10,000 values that I've put into a histogram, and that histogram has 20 bins. Well, you can use those 20 bins as a sort of discrete distribution which approximates your continuous distribution, and then use cont with the centers of those bins as the outcomes, and the cumulative distribution that you form from those bins as each one of these cumulative distribution marks in this side of this cont here, and then this cont line will end up approximating the data that you gathered, the continuous data that you gathered. So in short, if it's continuous data and there's no simple formula seems to fit, then take your data and form a discrete estimate where even every single outcome that you saw, even if every single one of them are unique, just pretend like they were discrete outcomes. And then from there, use disk or cont to end up implementing that histogram or that cumulative distribution function that you got from that raw data. All right, so with that, I'm going to end this section of the video. The next portion of the video will be opening up the Arena Input Analyzer and going through a tutorial of how to load data into it and then perform these fits that I kind of referred to earlier a couple minutes ago.